Hello and welcome. Today we are diving into one of the most powerful, and I mean really useful rules in all of calculus. It's the secret weapon that lets you solve all kinds of complex problems. We're talking about the chain rule.
So to see why this rule is such a game changer, let's just start with a problem. Take a look at this function. Seriously, how would you even begin to find its derivative? Your first thought might be, well,
because, let's be honest, without some kind of trick, your only real option is to multiply that whole thing out, 10 times, then simplify that absolute beast of a polynomial, and then use the power rule. That sounds awful. It would take forever. There has to be a better way, right? And thankfully, there is.
The whole key to solving this elegantly is to change how you see it. You're not just looking at one big, messy function. What you're really looking at is a function that's inside another function, and that has a name. It's a composite function.
And it's not as scary as it sounds. A composite function is simply one function tucked inside of another one. You know, kind of like those Russian nesting dolls, or maybe something a little tastier.
Yeah, a really great way to picture this is the M&M analogy. You've got the hard candy shell on the outside, that's your outer function, and inside you've got the chocolate filling, that's your inner function. The shell is literally containing the chocolate. You need both layers to have an M&M. And here's the kicker. Just like you have to bite through the shell to get to that chocolatey center, when we want to find the derivative of a composite function, we have to work our way through the layers. We deal with each part, one at a time, starting from the outside and working our way in. So this idea of working through the layers, that's exactly what the chain rule is all about. It's our elegant, super powerful solution to that messy problem we started with. And I absolutely love this quote from the mathematician Paul Foister. He says to think of it as a process rather than a rule. Forget about some scary, complex formula. This is more like a recipe or a simple routine. It's about building muscle memory, not just memorizing something from a textbook. So what is this process? It's actually beautifully simple. First, you take the derivative of the outer function. And here's the most important part. You leave the inside part completely alone. Don't touch it. Then, step 2, you multiply that whole thing by the derivative of the inner function. That's it. After that, you just clean it up and simplify. Now, for those of you who like the formal mathematical notation, this is what it looks like. If some big function, f of x, is really an outer function f with an inner function g plugged into it, then its derivative is the derivative of the outside, with the inside still there, times the derivative of the inside. It's saying the exact same thing as our 3 steps, just in math speak.
All right, enough theory. Let's actually put this into practice. We're going to use a little trick with our next example that makes seeing these layers super easy.
Let's check out the function y equals sine of x squared. This is a classic composite function, right? We've got an x squared function tucked neatly inside of a sine function.
A fantastic way to visualize this is what I like to call the box method. Just imagine putting that inner function, the x squared, inside of a box. So now our outer function is just sine of a box, and the inner function is whatever is inside that box. Okay, step 1. Differentiate the outside, but, and this is so important, ignore what's inside the box for a second. What's the derivative of sine of a box? It's just cosine of that same box. Notice we haven't touched the x squared at all. It just came along for the ride. Now for step 2, we multiply our result by the derivative of what was inside the box. Well, the derivative of x squared is simply 2x, and that's it. Put it all together, and our final answer is cosine of x squared times 2x. See? Just a simple 2-step process. Okay, you ready to go back to that monster problem from the beginning? Let's do it. Using our box method, what's the outer function? It's just box to the 10th power. And the inner function is all that polynomial stuff inside the box. We know exactly how to handle this now. And just look at how clean this is. First, we differentiate the outside. That gives us 10 times our box to the 9th power. Then we multiply by the derivative of the inside, which is 2x plus 5. And we're done. No multiplying it out 10 times. That is so much better. Now, this isn't just some neat trick for polynomials. The chain rule is, and I'm not exaggerating, probably one of the most useful differentiation rules in all of calculus. And that's because it opens the door to solving so many other types of functions.
Seriously, once you've truly mastered the chain rule, you can find the derivative of almost any function you're going to come across. Complicated trig functions, exponentials, logarithms, they all become solvable because they almost always have functions tucked inside of other functions.
It really is the key that unlocks the rest of differentiation.
But, with great power comes a few common traps. So let's look at a type of problem involving inverse functions, because the way they're written often trips people up. Here's a huge point of confusion. You see that little -1 exponent on sine, and your brain might immediately think, oh, that means it's a reciprocal. It's 1 over sine of x. But it's not. When it's written like this, it means the inverse sine of x. It's the function that undoes the sine function. And that's a really, really important difference. So at the end of the day, the biggest takeaway here is to always be looking for those layers. Don't get overwhelmed and try to solve the whole thing at once. Just like peeling an onion, you tackle it one layer at a time.
And that really leaves us with a final thought. This whole idea of breaking down a huge complex problem and just tackling it one simple layer at a time, that's not just a calculus thing, is it? What other big challenges, maybe in your work or just in life, could become a whole lot simpler if you just looked at them one layer at a time?